A single electric vehicle battery pack contains approximately 18 pounds of lithium and can store enough energy to power an average home for 2 days. Your smartphone battery, smaller than a deck of cards, holds enough power to make 500 calls or play 20 hours of video. These lithium-ion batteries have revolutionized modern life, powering everything from medical devices to power tools to massive grid storage systems. Yet just 30 years ago, portable lithium batteries barely existed, and the technology was considered too dangerous for consumer use. Today we're visiting remote salt flats where lithium is extracted from ancient brine pools and following the element through one of the most precisely controlled manufacturing processes ever developed to discover how unstable lithium metal becomes the safest, most energy-dense battery technology in history. Stay with me until the end, because what you're about to discover will change the way you look at every rechargeable device you own. Right here on Stories Behind Everything. Lithium is the lightest metal on Earth, and the third lightest element overall after hydrogen and helium. This extraordinary lightness, combined with its high electrochemical potential, makes it perfect for energy storage. Pure lithium is so reactive it ignites on contact with water and must be stored in oil to prevent spontaneous combustion in air. Yet this extreme reactivity is exactly what makes it valuable for batteries. Lithium's ability to give up electrons easily and accept them back creates the flow of electrical current that powers devices. The history of lithium batteries begins in the 1970s, when chemist Stanley Whittingham developed the first rechargeable lithium battery while working at Exxon. However, these early batteries had a dangerous tendency to catch fire. The breakthrough came in 1980, when John Goodenough discovered that lithium cobalt oxide could serve as a stable cathode material. Then in 1985, Akira Yoshino created the first practical lithium-ion battery using carbon as the anode instead of pure lithium metal, dramatically improving safety. Sony commercialized this technology in 1991, and the portable electronics revolution began. These three scientists shared the 2019 Nobel Prize in Chemistry for their work. Today, global lithium battery production exceeds 500 gigawatt-hours annually, enough to power tens of millions of electric vehicles, and demand continues accelerating as the world transitions away from fossil fuels. Everything begins with lithium extraction, and the largest deposits exist in two very different forms. Hard rock mining extracts lithium from spodumene ore found in pegmatite deposits, primarily in Australia. However, the most spectacular and cost-effective source is the vast salt flats of South America, particularly the Atacama Desert in Chile, and the Uyuni salt flat in Bolivia. These salt flats, some stretching for thousands of square miles, sit atop ancient lakes that evaporated over millions of years, concentrating dissolved minerals, including lithium chloride. The extraction process is remarkably simple yet time-consuming. Wells are drilled into the salt flat, and lithium-rich brine is pumped from underground reservoirs. This brine, containing just 5 to 0.25% lithium, is pumped into enormous evaporation ponds that can cover hundreds of acres. Under the intense desert sun and arid climate, the water slowly evaporates over 12 to 8. As evaporation progresses, different salts crystallize out at different concentrations. Sodium chloride precipitates first and is removed. Potassium chloride follows. Eventually, the brine becomes concentrated enough that lithium carbonate can be precipitated out through chemical treatment. The ponds are striking from the air, appearing as vast geometric patches of brilliant turquoise, yellow and white against the stark desert landscape, each color representing a different stage of evaporation and mineral concentration. The lithium carbonate extracted from brine or processed from spodumene ore is a white powder, but it's not yet pure enough for battery production. It undergoes additional purification to remove trace contaminants like calcium, magnesium, and iron that would compromise battery performance. The purified lithium carbonate is then converted to lithium hydroxide through a reaction with lime, creating a form that works better for certain cathode chemistries. At this stage, the lithium compound is ready to be transformed into battery materials. But the real complexity begins at the cell manufacturing facilities, where precision becomes absolutely critical. Modern lithium-ion battery production occurs in massive factories operating under conditions rivaling semiconductor manufacturing in cleanliness and control. The slightest contamination with moisture, dust, or metallic particles can create defects that reduce performance or even cause catastrophic failure. The process begins with cathode production. The cathode is the positive electrode where lithium ions are stored when the battery is charged. Multiple chemistries exist, but the most common for electric vehicles is nickel manganese cobalt oxide, known as NMC, or nickel cobalt aluminium oxide called NCA. These materials are produced by carefully mixing precise ratios of lithium hydroxide with nickel, manganese, and cobalt compounds, then heating the mixture to over 1,650 degrees Fahrenheit in controlled atmosphere furnaces. The resulting cathode powder is an extremely fine black material. This powder is mixed with carbon black for conductivity and a polymer binder. typically polyvinylidene fluoride or PVDF, dissolved in a solvent. The resulting slurry has the consistency of thick paint and must be perfectly homogeneous. Any clumping or separation would create performance variations. The slurry is coated onto thin aluminum foil using precision coating machines that spread it to an exact thickness, typically less than 0.004 inches. The coated foil travels through long drying ovens where the solvent evaporates, leaving the active material bonded to the aluminum. The dried coating is then compressed by massive rollers to increase density and ensure good electrical contact. The anode, the negative electrode, undergoes similar processing but uses graphite instead of metal oxides. Natural or synthetic graphite is ground to precise particle sizes, mixed with binder, and coated onto copper foil. The graphite serves as a host structure where lithium ions can intercalate, slipping between the carbon layers during charging. Some advanced batteries use silicon mixed with graphite to increase capacity, though silicon presents challenges because it expands dramatically when absorbing lithium. After coating and drying, both the cathode and anode sheets are cut into precise dimensions. For cylindrical cells like those used in Tesla vehicles, they're cut into long strips. For pouch cells common in smartphones, they're cut into rectangular sheets. Every edge must be perfect. A ragged edge or metallic burr could pierce the separator and cause an internal short circuit. The separator is perhaps the most critical safety component. This ultra-thin porous membrane, often less than 0.008 inches thick, keeps the cathode and anode from touching while allowing lithium ions to pass through. Modern separators are typically made from polyethylene or polypropylene and contain billions of microscopic pores per square inch. Many incorporate ceramic coatings for additional safety. If the battery overheats, the separator melts in a controlled way, closing the pores and stopping the flow of ions, preventing thermal runaway. The assembly process requires extraordinary precision. In a clean room with humidity below 1 to prevent moisture contamination, the cathode, separator, and anode are stacked or wound together. For cylindrical cells, the 3 layers are wound into a tight spiral, creating a jelly roll structure that's inserted into a metal can. For pouch cells, multiple sheets are stacked in alternating layers. Tabs are welded to the electrodes to create electrical connections. The precision required is remarkable. Alignment must be perfect to within thousandths of an inch. Any misalignment could allow the electrodes to touch. The assembled cell is placed in its container, either a metal can for cylindrical cells or a flexible aluminum laminate pouch for prismatic cells. Then comes electrolyte filling, a process conducted in extremely dry conditions. The electrolyte is typically a lithium salt, most commonly lithium hexafluorophosphate, dissolved in organic solvents like ethylene carbonate and dimethyl carbonate. This liquid allows lithium ions to move between electrodes during charging and discharging. The electrolyte is injected into the cell in precise quantities, and the cell is sealed immediately. The sealed cell then undergoes formation, the first charging cycle. This initial charge is conducted very slowly and carefully, while monitoring voltage and temperature continuously. During formation, a solid electrolyte interface layer, called SEI, forms on the anode surface. This layer is critical for long-term performance and safety. If formation is rushed, the SEI doesn't form properly, reducing battery life. After formation, cells are aged for several days while their voltage is monitored. Any cell showing abnormal self-discharge is rejected. The cells then undergo multiple charge-discharge cycles while sophisticated testing equipment measures capacity, internal resistance, and voltage characteristics. Only cells meeting strict specifications proceed to the next stage. For electric vehicles, individual cells must be assembled into modules and packs. A Tesla Model 3 long range contains 4,416 individual cylindrical cells arranged in modules. These cells are connected in series and parallel configurations to achieve the desired voltage and capacity. The Battery Management System, or BMS, is the brain of the pack. This sophisticated electronic system monitors the voltage and temperature of every cell or cell group continuously. During charging, the BMS ensures cells charge evenly, preventing any single cell from being overcharged, which could trigger thermal runaway. During discharging, it prevents cells from being drained too deeply, which damages them. The BMS also manages thermal systems, activating cooling when temperatures rise, or heating when cold weather reduces performance. Advanced systems can predict remaining battery life and optimize charging patterns to maximize longevity. The complete battery pack includes cooling systems, structural components, safety disconnects, and protective housing. A typical EV battery pack weighs between 900 and 1,200 pounds and represents nearly 40% of the vehicle's total cost. The chemistry happening inside a lithium-ion battery is elegantly simple, yet precisely controlled. During charging, electrical energy forces lithium ions to move from the cathode through the electrolyte and separator into the anode, where they're stored between graphite layers. Electrons flow through the external circuit, creating the current that charges connected devices. During discharge, the process reverses. Lithium ions flow back to the cathode, while electrons travel through the external circuit, powering your device. What makes this remarkable is reversibility. A quality lithium-ion battery can undergo this cycle 1,000 to 2,000 times or more before capacity degrades significantly. However, each charge cycle causes tiny amounts of degradation. Some lithium gets trapped in the SEI layer and becomes unavailable. The cathode structure gradually breaks down. The electrolyte slowly decomposes. This is why batteries eventually wear out. Safety remains paramount in battery manufacturing. Lithium-ion batteries store tremendous energy in small spaces, and if that energy releases uncontrollably, the results are catastrophic. Thermal runaway occurs when a cell overheats, causing internal chemical reactions that generate more heat, accelerating the reactions in a destructive feedback loop. Modern batteries incorporate multiple safety features. The separator shuts down at high temperatures. Pressure vents release gases before cases rupture. Current interrupt devices disconnect the cell if internal pressure rises. Manufacturing quality is essential. A single microscopic metallic particle bridging the electrodes can cause a short circuit years after production. This is why battery factories maintain semiconductor-level cleanliness, and why every cell undergoes extensive testing. Despite these precautions, billions of lithium batteries operate safely every day. The environmental considerations of lithium battery production are significant yet improving. Mining and processing lithium requires substantial water and energy. Cathode materials need cobalt, often mined in challenging conditions in the Democratic Republic of Congo. However, the industry is actively addressing these issues. New cathode chemistries reduce or eliminate cobalt. Lithium extraction from geothermal brines uses less water than evaporation ponds. Most significantly, lithium batteries are highly recyclable. At end of life, batteries can be disassembled and their materials recovered. Over 95% of lithium, cobalt, and nickel can be recycled into new batteries. As electric vehicle adoption accelerates, a circular economy is developing where old EV batteries are either repurposed for stationary storage or recycled to supply materials for new batteries. The next time you charge your phone or drive an electric vehicle, remember the extraordinary journey lithium has completed. Remember the salt flats where brine evaporates for 18 months under desert sun. Remember the furnaces firing cathode materials at over 1650 degrees. Remember the clean rooms where humidity must stay below 1% to prevent contamination. Remember the precision coating machines spreading slurry to thousandths of an inch. Remember the formation cycles carefully building protective layers atom by atom. Remember the battery management systems monitoring thousands of cells simultaneously. Lithium batteries don't simply exist. They're engineered through materials science of incredible sophistication, manufactured in conditions of extreme purity, and tested to standards ensuring safety across billions of charge cycles. They represent humanity's ability to harness reactive chemistry safely, to store invisible energy in compact spaces, and to enable a technological revolution that's transforming transportation and energy. And that battery in your pocket is a triumph of electrochemistry, precision manufacturing, and relentless engineering refinement. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you proper recognition for your contribution. Thank you for joining us on this exploration. Don't forget to like, subscribe, and stay tuned for more stories discovered through the smallest details.